Here is our basic equation. We set up a basic generic chemical reaction for an acid, releasing one of its protons and becoming its conjugate base. The definition of our acid was a molecule that will dissociate in water to release protons. We can set up an equilibrium constant, okay, which in this case we will call the acid dissociation constant, or K sub A. So we have our products on top. This is, of course, for our forward reaction, the dissociation of the acid into its conjugate base and a proton. So that's what's on the top. The acid is on the bottom. We said that if K sub A is very large, much, much bigger than 1, we call this a strong acid. It's dissociating completely in water. And our example was hydrochloric acid, or HCl. Alternatively, if K sub A was less than 1, such that it wants to stay more as an acid, this concentration is much bigger than the concentration of these on top. This is a weak acid. It does not dissociate appreciably in water, and our example for that was acetic acid. And so then if we take our equation for our acid dissociation constant here, we took the log of both sides, we pulled the pH term out based on the property of logarithms. We rearranged some things that we spent time last time doing that. For now, we're just going to show it to you. There it is, okay? The HH equation, okay? That says pH is equal to pKa plus the log in base 10 of the ratio of conjugate base to acid, right? So like I said, the proof is in the book, and we walked through the steps a little more in detail last time. Okay, so that P is essentially indicating, it has a more official, original name and meaning, like the potential of hydrogen, but for me, I just say negative logarithm in my head, so I remember it. Okay, so then pKa is taking the negative log in base 10 of the Ka. pH is the negative log in base 10 of the concentration of our protons, okay, our hydrogens. Okay. And so then the pH of pure water at room temp is 7, or what we call neutral pH. Section 10.13 of your text basically just proves this. And I mentioned this last time, and I'll just say it again, that I'm not going to ask anything about that section. I'm not going to ask anything about K sub W. This is like an equilibrium constant for the water dissociation. We're not going to talk about that. We're not going to use the phrase ion product of water. I'm just not going to talk about that. So you're free to skip that if you are reading along. 10:13. Any questions about this stuff? All right. We can just shout out the answers, I guess. Okay, so last time it said these were questions you turned in if you were here for participation. X and Y are acids, okay? And the acid dissociation constant of X is higher than that of Y. Okay, which is the stronger acid? So just as a group. X, yay, what was the reason? Just inspect it, look at it. High Ka means stronger acid. It will completely dissociate. This is the definition of a strong acid, okay? Which has a lower pKa. Also X, okay? So again, go ahead and think through it. I just put for us here, 1,000 was approximately the Ka of HCl, and 2 times 10 to the negative fifth was approximately the Ka of acetic acid, okay? So I just threw some numbers in and did an example, since it's the negative log, the acid dissociation constant, okay? pKa will be lower for our stronger acid, which has a lower pH. We have some X's. Everyone is in agreement with that? What's the reason for that one? That's the first thing I wrote. Intuitively, when we think stronger acid, we think lower pH. Alternatively, you can think through the same steps of doing the negative log of Ka, the negative log of the concentration of H. Which is, of course, now when you have a strong acid, the concentration of H plus is really high, it's bigger, it wants to dissociate down into its protons, whereas for our weaker acid, it won't. We'll have a lower concentration of protons. Okay, and you can do a quick mathematical example. The concentrations don't mean anything for us here, right? They have no effect. And then the final question was true or false. Both of these acids at 100 millimolar must have pH values less than 7.
False.
I have falses. I have a nodding for true. I skimmed your participation. They were split like half and half, so I know more people said true. Generally, this is true. Okay, by our definition, an acid dissociating in water, water having a pH of 7, an acid's going to give up protons in water, so it's going to drop the pH below 7 when it does that by raising the concentration of protons. It's not necessarily true, and here's a link if you want like a much more thorough explanation. Okay, I don't think they would ask something intended to be tricky that way. Especially because I agree that this is one that you could sell me either way depending on your explanation. Okay. Who got them all right?